And of concrete structures, double reinforced. Let's solve another example in double reinforced concrete section. So in this example, we have again a rectangular cross section with 14 inches times 24 inches with two of with F prime C of 2500 and the strength of a steel of 50,000 psi. So the very first part is a standing. I move to the table. F prime C is less than 4,000, so beta is 0.85. As soon as we know beta, let's assume that the compressive steel goes here and then check it later. Again, area of steel for calculation, we can call that AS2 or AS prime, which is 2 times 7, it's 1 inches squared. AS1 is AS minus AS2, 5 minus 1 point, which is 3.88 inches squared. And then you can calculate the height of this block, which is AS1, which is 388 times 50,000 of 85 is 2 point B. And if you do so, it just gives you 6.52 inches for height of witness block, and then location of a centroid C is a bit lower than A over beta 1, just 6.52 over beta 1, which is 8.85. It just gives us a centroid of 7.67 inches from the top of this section. So this is our 7.67 inches. Now let's see if the compressive steel yields or not. So epsilon prime S is C minus D prime, C minus D prime based off similar triangles. It just gives us 0.0020. That is higher Fy over Es, which is yield strength of grade 50 steel, and it's 0.017. 20 is higher than that, so it just says our compression steel in this example yields. So we do not solve it like a trial and error, and also something second degree equation to get the exact whatever we just calculated. A height of bit, that's the correct one. So tension and compression rebars steel are both at yield, so calculation of nominal moment, it's pretty simple, just add them up together. We have a portion of nominal moment divided 2 dissects to 2. The first part is, or one of them is Mn related to a steel, which is the pure steel for this part. This is the pure steel section, dissected to pure steel. And the other one can call the second one something like a combination of steel and concrete. We can call that Mn, nominal moment capacity related to the concrete, tensile steel. So if you the compression part, which is the pure steel, that's A prime S times Fy, because both of them goes for you. So both of them Fy applies to them. Then D minus D prime, and the other is 85% of F prime C times A times B is A over Mn is equal to, if you add them up together, that consists of total nominal moment. So let's see how can do the mass for nominal. So A prime is times Fy minus D prime. The first one, it just gives us 1 point times 10 to 6 pound inches for Mn1 or Mns. And the other part is, can calculate the second part based off each of them. So both of them are identical to each other. Concrete part at the top for the second part, that's correct, and that's exactly equal to if you just go for as minus as prime, which is as bar, f b minus a over. You can see the arm is completely the same. Forces are equal. The equations is the condition is in static mode, and the equations are summation of forces in x direction are equal to each other. So the force of concrete cancels with the force of steel bottom of the section. So if you do the mass from either of them, you can get the same numeric value of 4 10 to 6 pound inches, 4 times 2 10 to 6 pound inches. And if you just add it to MNS, you can just add them all together. It's for 0.23 10 to 6 and to convert it to kilo. So each 12 inches is 1 foot. Just gives you 475 kilo feet nominal density. And then we want to calculate the design moment, which is just phi times mn, which is mu. Then see if it's ductile. It can be allowed to use reduction factor. So it just gives you ultimate design moment 98 98.8 kilo feet. Just need to check the ductility. So from the minimum requirement for ductility case of ACI code is maximum of these two values. Our f prime c is 2500, so it's definitely less than. So this is the controlling second part of the equation for controls available. As over as, which is 5 times 40 times 20, which is 0.00, should be higher than rho minimum, which is 200 over 1000, which is f 0.0. That's done. That's less than that. Let's go for maximum ductility check based off rate 50, which is our problem. C over D. C over D should be less than 3.89. And if you the mass for C over rate 50, that's 7.67 or 24, which is the effective depth. That's 319, and that's less than allowed value in the ACI code version. So ductility check passes, so we are allowed to use 3.9 design calculation. Thank you. Solve more.